Okay, so thanks for joining us. Welcome to this last session about feedback and real-time classical processing for quantum applications. My name is Gal. I'll be moderating this session. I'm a physicist working with quantum machines. We have two speakers today. The first is Will Gilbert. Will is an electrical engineer. He's based in Sydney, Australia, so he's joining us bright and early for him. He's working on developing quantum dot qubits and scalable paths to fault-tolerant quantum computers with a group of Professor Andrew Durack at the University of New South Wales. And Will be presenting some of his nice results in a talk titled On-Demand Electrical Control of Spin Qubits. So Will, you can take it away. Thanks.
Thanks, Gal. Thanks for the kind introduction. It's great to be here, and thanks for the invitation to speak here at IEEE Quantum Week and as part of the Quantum Machines Workshop Day. Yeah, so the talk is titled On-Demand Electrical Control of Spin Qubits, and this is about some recent results that we've gotten over the past few months. So there we go. So just a brief summary to start. First, I'll just go over the quantum dot devices that we work with. And then I'll spend some time talking about these new results on electrical control. And then I'll sort of circle back and talk a bit about the control setup that we're using with the OPX from quantum machines and some of the real-time feedback protocols that we've been using with this system. And I can mention right at the start that some of these feedback protocols have really been enabling technology to get the qubit fidelities that we've achieved. So first, just a little bit of background on quantum dots. We work with silicon MOS technology, which is the same technology that's used to build the silicon transistors that we use for our computing technology today, which is based on a silicon substrate, an insulating layer such as silicon dioxide, and we pattern metal gate electrodes on top of this. And we apply a positive bias to these gate electrodes, which allows us to accumulate electrons and quantum dots in the silicon channel. We can detect the number of electrons and the charge state of these quantum dots by using a nearby single electron transistor as a charge sensor, which is very sensitive, allows us to accurately measure the charge occupation of the quantum dots. It also allows us to read the spin after we do a spin to charge conversion. So this is our qubit readout. And we're also able to control the spin using a nearby microwave magnetic fields. Traditionally, we deliver this using a microwave antenna. But as I'll show in just a moment, we're also doing this now using fully electrical control by delivering the microwave signals to a confinement barrier gate here, CV1. Okay, sorry for the massive amount of information on this slide, but a bit of background on the principle that goes into this control technique. So electrons in silicon have sort of 3 degrees of freedom that you can work with. The first is the spin. We can create splitting between 2 spin states by applying a static external magnetic field. You've also got a valley degree of freedom in silicon. And you get a splitting between valley states, which arises from roughness in the silicon dioxide interface. You can also induce a splitting using strain in the material, which is popular in other heterostructure technologies. And you've also got freedom in the orbital states. So you can actually as you add electrons to a quantum dot, the electrons fill in different orbitals, and this has been investigated in depth by a previous member of our team, Ross Leon, who actually showed you could operate qubits in all four of the s, p, d, and f orbitals of a quantum dot. But the interesting thing we're going to look at here is actually creating degenerate states of these degrees of freedom to create a hybridized state. And this allows us to get a strong spin-orbit interaction for the qubit, and this allows us to drive it electrically very efficiently. And this also follows on from some previous work, notably from CEA, from Andrea Corner, looking at spin value EDSR and some recent theory papers. So to make this work, the first thing we need to do is actually find a point where we have a degeneracy between states. And this can be a degeneracy between orbital states or a valley degeneracy. We think it works quite well both ways. But essentially what you can do is take this excited state spectroscopy measurement. So what we're doing here is measuring two charge transitions of a double quantum dot. Here scan versus the detuning between the double dot and the J-gate, the barrier gate voltage between the two dots. And so you see here on the left edge of this charge transition, we see this represents the energy of the ground state of this quantum dot. And just to the right of that, we see the first excited state. So if we probe this at low barrier gate voltages, where we have a low tunnel rate between the two quantum dots, we can see this splitting between the ground and the excited states. Now, if we extrapolate the trend between these ground and excited states, we can see that at some point these two states will become degenerate. So this tells us that for low J-gate voltages, we have some ground state here, we'll just call it A. And at some point, these will cross, where we have a hybridized state, a mixture of the ground state A and the excited state, which we'll call B. And then above this, at higher J-gate voltages, the ground state will be this B state. And we can use this in a control regime, so we can utilize this tunable energy spectrum. So to do this, we would start with an idling qubit in this A ground state. Then we can deform the dot by applying a voltage pulse to the J-gate to create a hybridized state of A plus B. And this creates a strong spin-orbit interaction and susceptibility to electric fields. So then we can apply a microwave pulse to rotate the spin. And then after that, return it to the idle state where it's then protected from decoherence. So this is what this looks like experimentally. My colleague, Dr. Tomo Tantu, developed this experimental protocol, which we've called pulsed electron spin orbit spectroscopy, or PESOS for short. And the way it works is essentially you apply a microwave pulse with a fixed power and time and scan versus the drive frequency and also one of the gate voltages, which we use to deform the dots. And this gives a simultaneous scanning of both the spin resonance frequency, the Lambda frequency of the qubits, and also the Rabi frequency. So we tune this pulse time to be roughly equal to giving us a pi rotation on a single qubit. And you can see here at low delta VP, we get a single rotation seen by just the bright peak. But the interesting thing here is that we see these sort of interference fringes where we see additional oscillations of this qubit for the same pulse time. So where this would be a single pi rotation, here we see 3 pi, 5 pi, 7 pi, and so on. We've just run a model simulation of this just to show the additional rotations of the qubit. And we can confirm that this really is a Rabi speed up by running this scan at a fixed microwave frequency and varying the pulse time. We get a more typical Rabi oscillation here. And you can see the speed up as we approach this point of degeneracy. So if we relate that back to this, this excited state spectroscopy diagram, we can map out this charge space around this dotted line where we think this degeneracy is. And if we do that, we can measure the speed up of the Rabi frequency and actually fit this dotted line, so we can see that this is exactly where the degeneracy appears in gate space. Now, we've actually found that this effect is quite reproducible. We've been able to replicate it in every device we've tried so far, in multiple different charge configurations and magnetic fields. You'll notice that the appearance of these degeneracies, we've called them X points, just simply because of the appearance. The appearance of these X points does vary quite a lot from device to device, and we think that this is due to the differences in the coupling between the hybridized states. So we get a strong coupling, you get a gradual transition across this X point, but say for device D, where the coupling is weak between the two states, you get a very sharp transition here. So now focusing on device D, I should say these results with devices A, B, and C are taken by delivering microwave signals through the microwave antenna. So it's primarily microwave drive, but there's a bit of parasitic electric field involved, and that's what's leading to this Rabi speed up. But now we want to drive this purely electrically, so we connect the microwave line to this CB1 confinement barrier gate. And this leads to some very interesting results. So now with device D in a particular configuration, we're able to get a very large speed up of the Rabi frequency with a minimum of well, it's not quite a minimum, we can get lower than this, but it's limited by the coherence time. We measured a range from 0.12 megahertz up to a maximum of 81 megahertz Rabi frequency. As far as we're aware, this is the fastest Rabi frequency that's been measured for electron spin qubits. I should note now that this is using the intrinsic spin-orbit interaction with the electrons. There's no micromagnets fabricated in this device. And that we think is quite interesting and important, since it could allow us to build dense qubit arrays with electrical control without needing to fabricate micromagnets into the device. Crucially also, with this type of spin-orbit interaction, we're also able to turn it off. And this is something that's not true of devices with micromagnets, which have a strong induced spin-orbit interaction. And also with hole technologies, where the holes have a naturally high intrinsic spin-orbit interaction, but of course you can't turn it off. We also looked at the magnetic field dependence of this effect. So we get quite a large speed up of the Rabi frequency at 400 millitesla, but we see a bit of change in the shape of this X point by changing the field. But we're able to replicate the effect across quite a large range of magnetic fields. In fact, we're limited in this set of experiments mostly by the electronics we had built into the setup. We see no reason in principle why we couldn't see this EDSR effect at a larger range of magnetic fields. So now we want to benchmark this qubit and achieve the highest fidelities that we can. So we actually achieve these at a higher magnetic field of 700 millitesla. And here we used Gaussian shaped pulses. You notice that this was quite trivial to implement using the quantum machines programming language, which is very nice to see. We did this since we were seeing some very close resonances in the qubit spectrum, and this allowed us to access them individually. Okay, so now we start looking at this qubit spectrum as a detuning from this degeneracy point. So we say this is a point of delta Vj equals 0. Then we measure the Rabi frequency with respect to this axis delta Vj. And we see an exponential dependence of the Rabi frequency on the detuning from this degeneracy point. We also see that the Rabi decay rate increases, so the decoherence speeds up as we approach the degeneracy point. But thankfully, we also see that the Q factor increases as well. We see a sweet spot around this 10 to 15 millivolt range in delta Vj. So now we select a control point of 14 millivolts in delta Vj and benchmark the qubit. So we did this using two techniques. The first is randomized benchmarking using the Clifford set. Here we achieved a fidelity of the elementary gate of 99.0%. We also benchmarked this qubit using gate set tomography. This is quite a new technique for us, and we're still learning more about it, but it provided a similar fidelity number, but with a bit more information about the source of these errors. Primarily, we're seeing errors in the identity gate. And this was I haven't got any graphics on it here, but this was these measurement protocols were developed in collaboration with Arthur Strauss from Quantum Machines and Galwana. And it uses some very interesting real-time pulse processing technology. Another thing we looked at is whether we can actually improve this identity gate by executing the idle time of the qubit at a point where the spin-orbit interaction is reduced so far away from the degeneracy point. So we performed this modified Hahn-Echo experiment where we always do the control of the qubit at the same point, but we vary the location of the idle wait time. And you can see that the coherence time is roughly stable at about 50 microseconds, but decreases sharply near the degeneracy point. So we think these are quite exciting results. Firstly, since it could enable dense qubit arrays with all electrical control and no need to fabricate micromagnets in the device where we need to do wiring fan out and things like that. But it could also have very important implications for long-range spin coupling using cavity resonators. And this is something that we're looking to explore immediately. So with that, I'll just switch gears a little bit. I just want to talk a bit about the setup that we're using with the Quantum Machines OPX. And this has been, using this system has been quite a paradigm shift for us, moving away from discrete AWGs and digitizers and signal generators into having a lot of these functions in a single box with a single high-level coding language. So we've managed to simplify our setup in a number of ways, including say being able to run our RF-SETs using purely the digital modulation and demodulation in the OPX without needing external mixers and RF sources. But also, most importantly, with the FPGA and the real-time logic, we're able to implement some fast feedback protocols So I'll just go over a couple of those now. The first is we feedback on the quantum dot chemical potential. This chemical potential is affected by charge noise, which is essentially traps and defects populating and depopulating in the silicon dioxide interface, which couples directly into the qubits. So you can see with the feedback off here, we map the location of a charged transition. You can see that it shifts around over the course of this measurement for about 5 minutes. But we can measure this in real time. This is done every shot, or on a shot-to-shot basis, where we measure the position of this charged transition and feedback by applying a gate voltage correction. And if we do that, we get a much more stable and reliable system. Now, we're quite inspired by some recent results from the group of Will Oliver at MIT Lincoln Labs. We showed some very nice similar results with a superconducting qubit, where they were able to cancel the 1/f noise by using real-time feedback, and we're pleased that we've managed to achieve a similar result here, where you can see in the blue trace here is the spectrum of the gate offset correction, which is applied to the quantum dots. And you can see at low frequencies, we see this increase in the noise, this 1/f spectrum. But measured in parallel is this green trace, which is the measured position of the charged transitions after that correction is applied. And you can see that it stays at the white noise floor rather than increasing at this 1/f trend. So we've expanded this to a number of protocols with similar, some varying techniques and frequencies, but this has been quite important for increasing the reliability and indeed the fidelity of our system. So one thing that's been important with this set of experiments is that the Rabi frequency and the qubit frequency actually couple in to the dot potential, since these parameters depend on the detuning away from the degeneracy point that are also affected by this low frequency charge noise. And you can see that here in the top left, if we turn off the amplitude feedback on the microwave drive, we see quite a lot of variance in the control of the qubit. So this is a measurement with repeated pi/2 pulses. And it's sort of like a discretized Rabi oscillation. But if we apply all of these feedbacks, then we get a much more stable and reliable system. And I should note that all of these are executed in real time and can be done at frequencies up to 2 kilohertz. With that, I'd very much like to thank everybody in the team who's contributed to this work. A lot of input has gone in particular from Dr. Tuomo Tantu, Andre Saraiva, Weihan Lim, Manke Feng. Thanks to the great team who's a pleasure to work with every day at UNSW. And also thanks very much to the support from Quantum Machines. It's really been a pleasure working with the team on almost a daily basis, talking about how to run our experiments and build new capability. So a special shout out to Gal Weiner, Jonathan Cohen and Arthur Strauss, and the rest of the team. So with that, thank you very much.
Yeah, thanks very much, Will. I can tell you that the feeling is absolutely mutual. It's been a pleasure. So do we have questions? I can see in the chat. Yeah, so there's two questions I see here. So one question about the gate set tomography. So was the gate set tomography protocols also implemented in QOP?
Yeah, that's right. Yeah, so the way we could do that is we create a gate set using the PyGSTI Python package, and then we actually do a translation of that into a simplified data format of pulse sequences, just as a list of pulses encoded as integers, and then we can, with the help of Ugal and Arthur, we were able to translate that into a real-time pulse processor. So we actually feed in the gate sequences, and then those pulse sequences are decoded in real time. So we use it to run randomized benchmarking and gate set tomography, but in principle, we can actually use the same technique for any sort of characterization with complex gate sequences.
Okay, thanks. And second question here. So what limits the feedback time on the last experiments you show?
Oh yeah, it's actually primarily the readout time for this system. With the current system, it's not particularly fast. We're working with readout times in sort of 100 microsecond range. So that's really the primary limit. Actually running the processing logic in the background happens of order a microsecond or less. So yeah, the main limit is our readout electronics.
Okay. Any more questions? Okay, I think that's that. So thanks very much, Will, again, for a great talk. Really, really interesting, beautiful results. And thanks for joining us.
Thanks.
Okay, so yeah, of course. So for our next talk, our next speaker is going to be Ramon Smook. Ramon is a physicist here at QM. He's based in France, and he's leading the company's AMO product efforts. Ramon's background is in cold atoms using atom chips, and before coming to QM, he worked on atom-based atomic clocks. And Ramon will speak about Rydberg atom arrays and tweezers, and some real-time feedback to do rearrangement of the atoms. It's really interesting stuff. Ramon, you can take it away.
Thank you, Gal. So can you see my slide? This is in the way. Yeah, it's clear. So hi, everyone. So my talk has two parts. It's mainly about classical feedback and things you can do with the OPX in this context. And the first example is how you can use the OPX to do atom arrangement. So to those of you who are not aware of what atom arrangement is and how it's performed, it's the scheme is basically in Rydberg arrays that you reflect a beam of an SLM or DMD device, which holographically generates an array of tweezer traps inside a vacuum chamber. And then the atoms are loaded into this tweezer array stochastically. So there's typically a 50% probability for an atom to be loaded into a single trap. And so initially, the trap look like this one on the left, unordered. And then on top of this static array, trap array, you superimpose another dynamical tweezer array, which is generated by two crossed AODs, which shift a laser beam based on the RF signals that are injected into them. And these RF signals originate from the OPX in our case, and are used to move beams around, pick up atoms and place them in their final destination to generate eventually ordered tightly packed arrays, as you see here. So the sequence is that you basically start by loading the atoms stochastically, as I said before, and then you take an image with a camera. And this image is processed using a PC or some other image acquisition system. And this image processing generates from the raw image an occupation matrix of the array. So it's a Boolean matrix, basically, with a 0 where there are no atoms and a 1 where there is an atom. And then this occupation matrix is transferred into the OPX, into the registers of the pulse processor. And we typically, we manage to transfer thousands, about 1,000 bits in less than 10 milliseconds. And then from this point on, the OPX does everything required to arrange the array. So each atom in the row is assigned to an oscillator, one numerical oscillator inside the OPX, and that generates a single tweezer. And we order the array row by row or column by column, and by picking up and moving all atoms in a single row simultaneously. So each atom will have a different tone associated with it, a different oscillator, and they will all be multiplexed, frequency multiplexed on the same line, going to the same AOD. Then the tweezer frequencies and phases are set to correspond to the atom position that we acquired with the camera. And then there is a dynamical multi-tone chirp waveform that is generated on the fly, that is calculated and generated on the fly inside the OPX with some QA code that I will show you in a moment. And then there's a pulse where these tones are chirped, and so ramped up at first, chirped, and then ramped down to place atoms in their final traps. So this is some macros. Gal talked about this in his session. That is basically the overview of the tweezer array code. So at first we assign tweezers to atoms. So we scan for each row. We do this for each row. For each row we find where there are atoms, and then for each atom position there is a corresponding frequency, and we assign to one oscillator this frequency and a particular phase so as to not introduce interferences. We then calculate the pulse length. I'll explain in a moment why you need to first do that. And based on this pulse length, you calculate the chirp rates for each one of the tweezers. Then you set the initial frequency and phases, and you can play the pulses. So the way that the play looks like, so the idea is that all atoms in a single row or column move together, but at different velocities. All atoms start at the same time and reach their destination at the same time, but they all have different velocities. And the idea is this is a typical technique used by the Michel Lukin group, is to have an optimal pulse for each row or column that you are ordering, that you're sorting. And the reason you want to do that is because there is a maximally allowed velocity for the atoms, so as not to introduce heating. And so you find which atom is farthest away from where it should be, from his target trap. And this largest detuning sets basically the length of the pulse for the whole row, because it's simply the detuning divided by the maximally allowed chirp rate or maximally allowed velocity. Yeah, so after you've done all this calculation, I'll show you some of this calculation in a moment, but just the bottom line is that after you've calculated all these chirp rates and the pulse lengths, you simply ramp up both the row selector or column selector and all the tweezers. This here is also a kind of macro where we're using Python to generate QA code. So this for loop here is a Python for loop, and it's just used to generate a bunch of play QA commands. So you ramp up with this ramp command all the tones in the correct location with the correct frequency corresponding to the location of the atoms, and then you chirp the atoms. So each tweezer has its own chirp rate. This is a vector, the size of the number of tweezers that you have. So they're all chirped, each one with a different chirp rate to move the atoms to their final destination, and then the tweezers are simply ramped down. So this is the actual code that is doing the actual playing of the pulse. On top of that, we have some more code to do the calculation. Let me show you a bit of that. First you run over all the tweezers that you have with a QOP for loop, and you assign the detuning of each atom, each tweezer from the initial position, the initial frequency to the target frequency, the target destination. And so you have a vector of detunings, and then you calculate in real time what is the maximum detuning, which corresponds to the atom, the detuning for the atom which is farthest away from its target. And then you calculate, as I said before, the length of the pulse for this particular row or column arrangement, which is basically the maximum detuning we've previously calculated, divided by the max rate, which is a constant. So this max rate here is a Python variable, for example, and max detuning is a QOP variable, showing that you can mix and match. The length of the pulse is in nanoseconds, so this needs to be cast into an integer, and you can do that as well in real time. So after you have the length of the pulse, you again iterate in a for loop over the whole tweezer vector, and you calculate for each tweezer j the chirp rate by just taking the detuning and dividing it by the length of the pulse. So this is basically all the calculations. So this, including what I've previously shown to play variable definitions and all the code to acquire the data from the acquisition system, it's around 200 lines of code. So as you can see, it really reads off like pseudocode. It's very straightforward. It's a high-level language. So now I just want to show you how it looks like. Can I play it? Here we go. So on the blue line, you see the waveform, and the pink one is the FFT of this waveform. And I've added like an internal loop to make it 1,000 times slower. And in this case, I think it's an arrangement of 9 atoms at the same time. So you'll be able to see at the tone starts, and then with the FFT, you can see that everything chirps smoothly. The fact that you don't see any skirts in the FFT indicates that there are no phase jumps and no dead time in between pulses, and that everything is nicely phase coherent. I could zoom in and show you the actual pulse, but I think this is convincing enough. So this is the basic demonstration for atom arrangement. So this is the arrangement of a single row, right? And then you would have that in an external for loop and do that row by row. And all in all, it's quite straightforward. But the fact that a simple atom arrangement protocol takes only 200 lines of code and is quite straightforward to write, opens the possibilities to write more advanced sorting algorithms using reservoirs of atoms, refilling defects in the array as they occur. So currently, really the bottleneck is the detection time of the camera and basically the physics, the velocity with which you can move atoms. Yeah, so let me, with that, move to my second example. And that's real-time parameter stabilization, which we'll kind of discussed about with lower frequencies. So he was limited by the physics, again, of his acquisition, which was, as he said, hundreds of microseconds. Here I'll show some examples of what you can do in the other extreme case where you are not limited by the acquisition time of the system. And this is a typical use case in AMO, and that's the stabilization of laser intensity, but it could be applied directly to any kind of parameter drift or noise. So a feedback loop implemented in QA, the toy PID code that I will show you now, can typically react with a latency of below half a microsecond. So the code you see now, I think it's like 350 nanoseconds also to do all the calculation and everything. And so latency, we define it as the time elapsed from the last acquired sample of the error signal or the sensor that you, the signal that you want to feedback on, to the first generated sample of the corrected signal that is sent again to the system. So if you can do less than half a microsecond of latency, that implies a lock bandwidth of above 250 kilohertz. So what you will see now is something on the order of 350 kilohertz. And this can be used for to generate what we call adaptive gates, as opposed to robust gates, which people know from optimal control. And this is a complementary approach to optimal control. Both will be needed. The idea is that in optimal control pulses, you can generate pulses that are immune or robust to certain fluctuating parameters, such as laser frequency noise or others. But typically, these optimal control pulses, or sometimes they are rendered more sensitive to other noise sources. So a typical example is well-known optimal control pulses in AMO that eliminate or mitigate, reduce sensitivity to laser frequency noise, but at the same time increase the sensitivity to laser intensity noise. And as Miri showed us also at the beginning, laser intensity noise is indeed currently one of the largest bottlenecks, the largest contributors in the noise budget for gate fidelities. So the experiment I've done here in the lab next door is a simple, straightforward one. You can do much more advanced stuff, but I want the code to be simple. And that's maybe a recurring theme of this demo, is to show that simple things are simple in QA. So what I did, I generated a train of 100 nanosecond Gaussian pulses, 100 nanosecond being a typical gate time in Rydberg arrays. And then these are sent to a power detector, and the envelope of these pulses, the intensity profile of these pulses, is then integrated with the OPX, and the value of this integral is compared to some set point that the user defines, and the system in a feedback manner locks the integral of these Gaussian pulses to a certain value. So as you see here, so the latency here, so this time scale is 200 nanosecond per square, so it's a bit, so from the end of the pulse to the beginning of the previous one, we have a bit less than 400 nanosecond. And then, so each point in this graph, and in the graphs you'll see later, is the integral of the intensity of one such Gaussian pulse. And so within a few shots, we stabilize the intensity to a set target. So we reach in about a microsecond or so the set point. So this is the whole code that I've based this demo on. It's 20 lines of code, 15 of which are QA. Like 1, 2, 3, 4, 5, 6, 7 of them are variable definitions, and then here it's a typical PID code implementation. So first we measure this Gaussian, we measure the Gaussian pulse on a power detector. So we play first a Gaussian pulse with a scaling of the amplitude, and the scaling is given by this QA variable called amplitude. So we play this to a laser, and the laser is associated with some power detector, say, and then we take the profile that was measured, and we perform an integration, and the result of this integral is stored into this other QA variable called integ. And then we assign the equal sign for in QA, and then we assign the target set point minus the integral, and then we bit shift it a bit to have a nice dynamic range. This takes very little latency, and we store the error signal basically into the QA variable called error. And then we generate an integrator, the integral part of the PID. by setting some alpha, which characterizes the memory of the PID loop. And so the integrator error accumulated up to this point is multiplied by 1 minus alpha. Alpha is 10% here. So all the history is attenuated by 10%, and then the new value is multiplied also by 10. The new error is also multiplied by 10%. And this is a typical implementation of an integrator in fast digital PID loops. It gives an exponential decaying weight into the past, and it gives very similar results, or even better sometimes, than just saving all the history and taking the sum. We then calculate the derivative part, which is the old error minus the new error. We update the old error to be the new error, and then we calculate the new amplitude, which is the old amplitude plus the proportional gain times the error, the integrator gain plus the integrator, and the differential gain plus the derivative. And then we do that 10,000 times. And at some point it will, and this locks, right? And so what I'm saying by latency of 300-400 nanoseconds is all these calculations between the measure and the one after that. And that basically sets the lock bandwidth, right? And so this is a simple example. So what I did is I did this thing. So again, each point here is a Gaussian, is the integral value of a Gaussian wave packet. And I've added a sideband 50 kilohertz away, so it generated noise at 50 kilohertz. And at this point here, at 750 microseconds, I turned on the lock, and so the lock manages to reduce this noise basically to the detection noise, which was not very good, I must admit. But 50 kilohertz is easily within the bandwidth of this lock. And you can, of course, optimize PID parameters. I did that a little bit with reasonable results. You can also write a QA code that optimizes the PID parameters. So these gain for the PI and D, they in principle can also be QA variables, and they can be adapted in real time. You can do more fancy stuff. I just wanted to show you the 20 lines of code version of this. Yeah, and so if you would do that, you would have a more robust lock that adapts, and this goes in the direction of Kalman filters and so on. So increasing the frequency of this noise is simple. I went to 200 kilohertz, and then we don't manage to reduce the noise completely because we're starting to approach the end of the bandwidth, but we still get about 10 dB. So a factor of 3 on the amplitude, and thus 10 dB reduction on this power spectral density component at 200 kilohertz. Again, here I start the lock, and I managed to reduce the thing. So it's safe to say that the lock bandwidth here is several hundreds of kilohertz, certainly above 200. So this is a simple example. You can do better than this. My detector is not the greatest thing in the world. What I have here, it was just for a demo. And we have done with clients, and we've researched things such as Bayesian estimators. You can do Kalman filters, machine learning-based filters. It's a high-level programming language that resembles Python. You can write whatever you want, and then it will run with this kind of bandwidths from a high-level programming language. So the takeaway message, the conclusion is, in quantum processors, the circuit will become deeper, stabilizing the circuit over many gate iterations while maintaining the fidelity will require this kind of adaptive gates, laser display, temperature drifts, acoustic noise. You have noise that are particular, noise within 200 kilohertz that are particular to different kinds of lasers, and to be able to run circuits on concatenated list of gates with running up to 100 microseconds, 1 to 100 microseconds will require this kind of adaptive gates to preserve the fidelity. And then going back again to what Will kind of said, so shot-to-shot fluctuations, of course, which in Rydberg arrays are very long, so above several hundreds of milliseconds. So temperature-related drifts, humidity you sometimes see. These are easily within the bandwidth of such logs, and so this will just generate a more robust and optimal sequence, and it doesn't have to be for quantum processors. For any AMO experiment, you would win a lot of stability and pain by having something that simply adaptively logs the critical parameters. And what we've seen with clients in AMO is that in many cases the limiting factor in the feedback bandwidth is actually the experimental system, not our control hardware. And typically it's simple fixes. In AMO physics, people are used to using sequences on the microsecond timescale, right? 1 megasample per second is very typical in all the current AMO labs. And so things in the lab are filtered accordingly. Photodiodes are sometimes filtered at 10 kilohertz or 1 kilohertz even, because there was never, or 1 megahertz, because there was never really any need for that. They were just used as, shot-to-shot stabilization circuits. But now that you can do things like that in real time, it's worthwhile to invest in a fast photodiode with some 100 megahertz of bandwidth, so that you can correct properly these kinds of fluctuations. That's it for me. Thank you for your time. If you have any questions, I'll be happy to answer.
Thanks very much, Ramon. Let's see if there are any questions here in the background. So here's one question.
Yeah. When you get to the, so can you do this laser stabilization in parallel to doing other things? Yes. Or do you need to interleave it with the experiment? Good question. So yes, of course. So this was what I've shown you is a snippet of 20 lines of code that you can put it wherever you want in your sequence, right? You can make a macro out of it and call it laser stabilization. And then every time in the sequence that you feel that you need better stability, you just write one line of code and your laser will be stabilized to orders of magnitude better, depending on the noise process. Of course, yes, that's the whole point.
Okay. Any more? Okay, so I guess this concludes our session. It's now very late in both France, Bordeaux, where Ramon is, and Tel Aviv, where a lot of us are. So good night from Tel Aviv, and I hope you have a successful continuation of your day wherever you are.
So,
thank you and goodbye.
Bye-bye.